Imagine two systems for handling mistakes. In the first, if a single piece moves out of alignment, the system crushes it to maintain order. In the second, if an anomaly appears, the entire system shifts its shape to fit the new reality. This contrast defines the word law. It began as a set of prescriptive commands handed down by authorities, and it was only much later that scientists adopted the term to describe the physical world. We call the first type normative laws. These rules prescribe how people should behave, like ethical codes or antitrust regulations. When a person's actions contradict a normative law, the person is punished. The rule remains, and the actor faces a sanction. Scientific laws work differently. They are descriptive regularities that detail how the universe and human behavior actually operate. Here, the accountability is reversed. If empirical evidence contradicts a scientific law, the law itself must be modified or discarded. Normative laws dictate what ought to be, but scientific laws are forced to adjust to what is. This distinction leads to grounded rules, prescriptive guidelines that aren't just arbitrary commands. A grounded rule is a decision model built specifically on the foundation of established scientific laws. The marketing concept functions this way. It's a business philosophy that advises firms to integrate their activities and focus on customer needs based on the observed relationship between these actions and long-term profit. Scientific laws provide the structural account of a system that makes these grounded rules effective. Understanding the laws allows us to predict the outcomes of our decisions. To gain that predictive control, however, a proposition must first prove it is actually a law. A statistical pattern in a dataset isn't enough. It has to pass through 4 rigorous gates. Many researchers fall into the trap of assuming that big data and high correlations automatically create scientific laws, but correlation is only a starting point. To reach the status of a law, a statement must pass through a specific 4-gate filter. Gate 1 is a matter of structure, the generalized conditional. The statement must take the form of if, then, or all A are B. This hierarchy shows generalized conditions are the base level. If formatted correctly but untested, they become law-like generalizations. With substantial empirical testing, they become laws. At the very top are principles, laws forming the core of the field's knowledge. The if-then format of Gate 1 is a prerequisite. If a statement is formatted correctly, we can begin to test it against reality. Gate 2 requires empirical content. We distinguish between synthetic statements, which require observation to verify, and analytic statements, which are true by definition alone. Analytic statements are tautologies. Because they are true regardless of what happens in the real world, they tell us nothing about reality and are scientifically useless. A statement like, all retail stores that sell goods are retail establishments, is technically true but empty of content. Gate 2 rejects it. Synthetic statements pass this gate because they take a risk. They make a specific claim that could be proven false by looking at the facts. To be a scientific law, a statement must be capable of being wrong. Gate 3 is Nomic Necessity. This gate prevents accidental generalizations from being mistaken for laws just because they happen to be true at the time. We test for this using the counterfactual conditional, a hypothetical what-if scenario. Take the accidental generalization. All the screws in Smith's car are rusty. If we put a brand new screw in Smith's car, it doesn't instantly rust. It was a coincidence, not a law. Now consider all heated copper bars expand. Even if we don't heat this specific bar, we know that if we did, it would expand. The property of the material guarantees the outcome. Scientific laws describe the fundamental properties of a system. Unlike coincidences, they allow us to predict what will happen in the future. The final hurdle is Gate 4, systematic integration into a body of knowledge. Even passing the first 3 gates and having data only makes a statement an empirical regularity until it connects to a broader theory. Andrew Ehrenberg's duplication of viewing relationship, the DV relationship, is a case study in why data alone isn't enough. Hundreds of empirical cases backed the DV relationship. Statistically, it was a robust, consistent pattern, but it failed Gate 4. It existed in a vacuum, failing to integrate with any theory of consumer behavior, and didn't explain why the pattern existed. Compare that to Shapiro's work on price and quality. Those relationships became law-like because they were deduced from established cognitive theory, fitting into a larger map of how the mind works. Data without theoretical integration is just a pattern. To be a law, a proposition must be part of an integrated system of understanding. If these empirical regularities aren't laws, should we ignore them? No. Regularities are vital for scientific discovery, as the case of Edward Jenner illustrates. Jenner noticed a specific regularity. Milkmaids almost never contracted smallpox. That pattern wasn't a law itself, but it provided the clue Jenner needed to investigate the cowpox virus. Following that clue led Jenner to the discovery of the smallpox vaccine, saving millions of lives. Empirical regularities are rarely the final destination, but they are often the spark that begins the investigation. This creates a divide in research over where scientists should actually start. The ETET approach, empirical to theory, argues that we should find the regularities in the data first and then build the theory. Researchers like Ehrenberg champion this bottom-up, data-first methodology. The TETET approach, theory to empirical, argues the opposite. Start with axioms and theory, then test them against the data. Researchers like Frank Bass champion this top-down methodology. Shelby Hunt's scientific realist perspective suggests that science doesn't require a single starting point. Mining data for regularities and deducing theoretical axioms are both valid ways of expanding what we know. The starting points are different, but the goal is the same. No matter how a claim begins, it must survive the 4 gates to become a scientific law. Only then does it provide the basis for the understanding and control necessary to navigate the world.